Hello everyone, I'm Philippe, the VP for Strategy and Marketing at Mersen, and I'm glad to co-author this paper with Jean-Francois de Palma, who is the VP R&D and Innovation in the same division. So today the paper will be about the innovating cooling solutions for the wide bandgap devices, more specifically Silicon Carbide, and we'll show you the way we can dramatically improve the thermal management of such devices. What I want to also highlight is that over the last 20 years, there's been an incredibly huge increase of the power density. If we look at these are data coming from Infineon, the evolution from the IGBT second generation to the SIC MOSFET, the power module power density has been multiplied by 5 over the last 2 decades. If we look at power inverter, it's even a factor 10 over the last 2 decades, as you can see, as compared to the last BGTs based inverter, and then the IGBTs, and now SiC and GaN, where you can see that the power density expected is just amazing. So for sure, this has a lot of impacts regarding cooling. It is important to really compare both silicon and silicon carbide, the power density as a function of the die size. On the left-hand side, we have the die width as a function of the current, and for a given current, here, for example, 100 amp, you can observe that the chip area is approximately 1/4 the one of the exact same silicon IGBT. On the right-hand side, we observe both the power losses density in watt per square centimeters as a function of a current rating, where altogether we can see that SIC MOSFET has power density losses, which is approximately twice as compared to silicon. So as a conclusion, what we can say is that the cooling solutions must now manage twice more losses from chips that are 4 times smaller. So let's enter inside the power module. So you will know that from the chip, from the silicon carbide chip or any kind of material, the junction temperature is then going through a series of stacks made of encapsulant, die attach, substrate, base plate, until really touching the heat sink. And it is easily demonstrated that the temperature of the base plate is the junction temperature minus thermal resistance times the dissipated power. So if we look to this from another angle, it can be easily demonstrated that the junction temperature to the base plate is really a question of the thermal resistance times the power. So here, for us, it means that we don't have necessarily to take the junction temperature as the reference for the temperature we will have to cool down, but the heat, the heat we will really see will be the one at the base plate location, and that's the one that is very important. So this kind of, I would say, sandwich is simply, let's say, decreasing a bit the junction temperature, but still at base plate level, we see a lot of heat. So the junction temperature is very important, and we were expected so far a very huge increase, a steady increase of both silicon and silicon carbide junction temperature, and we were expecting, or the scientific community were expecting that we can easily exceed the 200 degrees C for SiC, for example, because theoretically it can reach such a value. But in reality, what we observe in the real world is that first the silicon tends to plateau around 150, 160, 170 maybe, whereas silicon carbide obviously won't exceed 100 degrees C. There are plenty of reasons explaining that. First, it's not just a question of having a chip that can reach high junction temperature. You have to adapt all the surrounding components, material, polymers to that. And it is well known that a power module is made of gel. There is a gel filling, there is the housing, which is made of polymers, and that it's hard for them to really sustain such a high temperature. We all know that the oxide layer tends to degrade at higher temperature in SiC MOSFET, which is very, very bad for sure. We also know that overall the conversion efficiency tends to decrease as temperature increases. So in the end, what we estimate is that we should normally not observe TJ silicon carbide commercial device exceeding 200 degrees C. And for us today, the upper limit we use to work with is rather 180. So looking at key applications, we saw this trend, whereas there are some application now reaching 175 degrees C, like PV inverters, EV, routinely, I would say. More on the industrial side of the business, we are still in the range of 150. The only exception comes from the aeronautics and some oil and gas, very specific application for which 200 degrees C can be achieved. So let's see some very important impacts of the silicon carbide on surrounding devices and components. Here you have two axes. One is the normalized system size, meaning the size of the inverter. The other, the y-axis, is about the losses, in other words, the efficiency of the conversion. So if we first position full silicon IGBT and silicon diode inverter with a switching frequency about 4 kilohertz. It typically used so-called standard cooling. It could be cables, it could be connected with bus bar. It's standard caps and standard fuses normally. Then we started implementing SiC diodes, so we were substituting a silicon diode with SiC diode, but keeping the same switching frequency. And quite naturally, it helps to start shrinking a bit the dimensions, the system size, and at the same time tends to decrease the system losses. Here, for this particular setup, we start seeing interest for small dimension cooling. It could be laminated busbar, it could be advanced fuses and advanced capacitors, either film or electrolytic. And then came the full SiC, and in that case, I just took an example of 16 kilohertz switching frequency, where definitely there've been a need for advanced small dimension cooling, very low inductance busbar, low inductance fuses, and also definitely film capacitors. And then people try to play with the switching frequency. So at the same time, yes, the system size tends to shrink and shrink again, because most of the passive volumes and size were also shrinking. At the same time, since we are increasing the switching frequency, the losses tends to increase a bit. So here at 24 kilohertz, if we try to draw 48 kilohertz, so same trend. And the kind of holy grail is really reaching 100 kilohertz, for which definitely there'll be a need for high power density specific cooling, ultra low inductance busbar, super low inductance fuses, and a high temperature busbar and film capacitors. And once again, I recall you that we are here typically where we are facing 180 degrees C junction temperature. So before introducing what we can do with a heat pipe, embedded heat pipe, let me introduce what's a heat pipe. So a heat pipe is basically a two-phase heat transfer tubes, as you can see here, made of a casing, and width is copper in general, and there is internal capillary wick inside that helps for the vapor transportation. So if we do locate the heat source, typically the power module, on one end of this tube, of this heat pipe, it will naturally create vapor, and the vapor will be then transported all across the tube until the other end, and here the other end will naturally tend to condense this vapor into a liquid, and the liquid will get back, in fact, to the evaporator left hand side by a basic capillary transportation means. That's really the way it works. So it's really a continuous back and forth of the vapor here. So what we've done with heat pipe, we have embedded heat pipe in a standard heat sink. So as a reference, in the middle you can see the so-called aluminum blank heat sink, which is the very regular standard heat sink technology. On the top you have the exact same design but made out of copper, which by essence should exhibit much better thermal conductivity. And on the left hand side bottom you have the same aluminum blank design but with embedded heat pipe. On top of those heat sink we do locate and place a power module, and we just observe the temperature rise just underneath the module. And here are the results. As you can see, in fact, we do observe that there is a minus 30% less temperature rise when we are comparing heat pipes, embedded heat pipes with standard aluminum blank. And we can even demonstrate that embedded heat pipe on aluminum heat sink gets even better, in fact, performance than the same copper heat sink. Given that, first, cost-wise, copper heat sink would probably cost a factor 4 more than a standard aluminum one, whereas the aluminum plus embedded heat pipe is only, as you can see, 25% more expensive, whereas the weight would be probably 3.5 times more heavy for copper, and is almost the same for aluminum heat sink. So it shows how important it is, and it works very well. Here we can demonstrate that the embedded heat pipe really is a heat spreading technology that helps better use the entire surface area of a heat sink, and the heat is really extracted by each and every things. So this video is probably the most obvious demonstration. On the left hand side you have a blank heat sink here, okay, standard one, and on the right hand side this is the exact same design but with embedded heat pipe, but more precisely inserted inside the base plate. Okay, so it's an additional feature we are putting here. So if I launch the video, you will observe that on the left hand side, on the blank heat sink, there is a very huge hotspot that is happening, whereas on the right hand side, thanks to the embedded heat pipe, no hotspots. Once again, the heat is perfectly well spread over the entire area of the heat pipes. So in the end, we also observe that there is a rise of temperature which is approximately 10 degrees more here as compared to the one with the embedded heat pipe. So really, embedded heat pipe can turn any kind of standard blank heat sink into a very high performance air heat sink. So we did some simulation as well in order to try to understand what could be the influence of the power module position, and we try with several setups, so locating the module on the leading edge, in the middle, on the trailing edge, and we simply measure the normalized delta T, so the temperature difference, as I told you. And as you can see, there is almost no impact on the thermal performance. So wherever the module is located, the heat pipe is doing its job very well and is spreading the heat once again all across the base plate. So also, what is interesting is it's not only to be able to insert and glue heat pipe, is to make sure this will last long time. It's a question of reliability, and for this we perform several tests. One was dealing with shock and vibes according to the IEC 61373 norm, and another one was a thermal cycling from -40 to +100 degrees C, which is dealing with the railway specification. And we observe both the thermal resistance and the flatness before and after this test. So let me show you first the result regarding shock and vibes, and as you can see, there is only a small variation of the thermal resistance of less than 2% before and after this very stringent test. Now, if we look at the thermal cycling, here it's almost negligible. Even after these very tough cycles, minus 40, plus 100 degrees C, there is a variation of less than 0.5% of the thermal variation and almost no degradation observed for the flatness. So it means that really this technology is now fully mastered, it works well, and there is no degradations observed over time. So another important point was also to demonstrate how simulation can help, because it's not just a question of manufacturing it, but just being able to anticipate the performance of these devices. So here we have developed a very special toolkit to simulate that, which is not based upon thermal conductivity core as usual, but it's rather based on vapor thermal transportation modeling. And as you can see on those two graphs, so those two are related to either a 12 millimeter heat pipe or an 8 millimeter end pipe, either inserted or embedded in a heat sink. It shows an error that is less than, I would say, plus minus 5% from the simulation to the real experiment. So it shows how accurate it is, and it demonstrates that we can really perform and anticipate the performance of the heatsink even before manufacturing it. Now let's move to rather liquid cooling. So far we were talking about air cooling. Liquid cooling made a lot of progress also to better adapt to silicon carbide. So here it's a technology branded ISOMAXX, which is the ultimate liquid solution for power module. So in that case, the expert would have recognized that this is not SIC, these are silicon IGBT prime pack, but it works the same for SIC. So if we look inside the plate, we'll observe that we have designed and patented these very specific, I would say, channels, fluidic channels. It's a kind of, if we zoom in, it's a kind of spiral, wavy spiral, which the fluid is transporting in, and that can be located exactly where we want. So the idea is really to locate those spirals just underneath the chips itself. So first we have to know where are the chips located, and then as long as we know where they're located, we can really adapt the design in order really to locate those spirals just underneath and being able to extract the heat exactly where it should be. So as a result, it's not only that the thermal performance is better, we are here demonstrating 6 degrees C per kilowatt thermal resistance, but you can really get almost no temperature difference from module to module, okay, which is already very good, and also, which is almost more extraordinary, no temperature difference from chip to chip inside the modules. And this has a strong impact for our customers, meaning that they can locate the modules closer one to the others. So as a conclusion, I would say that now the wide bandgap have reached definitely the maturity level at semiconductor level. The problem remains the passive surrounding components, capacitors, magnetics, and of course thermal management. We can help our customer co-design things in an optimized way. This is what we do. We just don't sell only standalone components. And the idea is really to help our customer to better design silicon carbide based technology with this kind of product and new innovation all together as one. So that's really what we want to do, facilitate the journey of our customers in modules or inverter design. So time for me to say thank you for your attention, and I hope to see you very soon.